Hi everyone, good morning. I hope you're somewhat awake. I hope I'm somewhat awake, we will see. So I'm Michaela, and today I'll tell you a little bit about what I do and maybe what you can also do. So from what I understood, you're still very young astrophysicists, so maybe it will be interesting for you to see some of these opportunities. The reason why I'm doing this presentation is because many times when I talk to people about what I do in my PhD, they're a bit confused because I am actually an engineer. I graduated as an aerodynamics engineer, working with high-speed flows. But then I started doing solar physics in my PhD. Now we're doing mostly space weather modeling, but we still work with hypersonic people, and we also work with fusion people. And people kind of don't really maybe get sometimes how that works. And this is something that I want to kind of also bring up with you, because if you learn plasma physics, if you learn how the dynamics of the hot fluids behave in the presence of electromagnetic fields, there is a lot that you can do still related to space. And okay, maybe it will take sometimes a little bit more reading, but you have many opportunities that are out there, so I want to show you some of them. Of course, some of them, there is many more, but I want to show you those that I actually was in touch with or that I experienced myself. So here you can also see my email in case you have questions later. So if you imagine plasma physics and astrophysics, does this change? Yeah, you probably imagine some kind of a nice nebula, and you can indeed use numerical plasma physics to determine the expansion of these kind of things and how they form supernova remnants, shocks, etc. And that's all very nice. But there is much more than that, right? So we have the astrophysical plasmas, for which you can already use your knowledge to describe how this will behave. But we have many other fields, and I will tell you a little bit about solar physics, right? That's kind of where I started with my PhD. Then also kind of applied solar physics, which is space weather forecasting. Now, maybe not many of you are really interested in the applied term too much, but if you're looking into places where you have a lot of funding these days, a lot of money by the EU, then space weather is up there. A little bit of aerospace, so that's not just astrophysics, right? But it is still, I think, very interesting, and maybe some of you will find your interest there. And in the end, some fusion. So solar physics, this is actually probably the most related to the plasma physics that you had at the university, right? I really have to promote the Rosseland Center for Astrophysics in Oslo, where I was for a couple of months last year. And what they do there with plasma physics, so once you understand, of course, with plasma physics, you can look at kinetic equations, but you can also look at fluid equations like Navier-Stokes, combine it with electromagnetism, and we're trying to understand how the sun works. Now, you know this probably very well. It's a very embarrassing how little we know about the sun, right? It's right there, we can observe it very well. We're literally, well, it's the closest star, right? And we still do not understand phenomena such as the solar dynamo. We don't understand a lot of flux emergence. We don't understand coronal heating, right? And you can observe these things as much as you want, but at the end of the day, if you really want to show that we understand the processes and how this works, you have to put it into the model, and you have to show that your model reproduces the observations. That's also why I think numerical physics is so interesting. So what they do in Oslo, they have very advanced plasma physics codes. One of them is, for example, Bifrost, where they look at the solar magnetic field and they try to replicate the motion of the plasma in the photosphere, in the convection zone. And then from the photosphere, they determine the radiation field and compare that to observations and see if it matches or not. They're now also starting a whole sun project where they're trying to replicate the solar dynamo. I think it's very interesting, and it's definitely one of these things that, from what I've seen, most solar physicists, at least in the numerical part of it, they don't do solar physics just because it's interesting, but mostly because it's frustrating that at this point of our technological development, we understand so little. Now, obviously, it's interesting and frustrating, these kind of problems that we have with solar physics, but it's also dangerous for us, which is why we have the application of space weather. I'm trying to change the slide, yes, which is actually what I'm doing now mostly within my PhD, that I do at KU Leuven. It's near Brussels in Belgium, a nice university. You can drop by if you want to ever give a seminar. We have very good waffles and very good fries and a lot of beer. Anyway, space weather. So you probably know this again very well. We have all sorts of different flares and coronal mass ejections coming from the sun. Many times because of these processes that we do not understand, we cannot predict. But despite the fact that we can't predict them, they still hit us, right? This kind of coronal mass ejections, many times they make it all the way to the Earth, and then we have a problem. Not that many so far. Since the digital age started, we haven't had any very, very strong, we call it Carrington events. But we have seen, for example, in 1989, there was a 9-hour power outage in Quebec, in Canada, as a result of a geomagnetic storm due to these coronal mass ejections. We have seen many times the air traffic has to be grounded because of telecommunication problems during geomagnetic storms. Last year, Elon Musk's 40 satellites burned up in the atmosphere. By the way, if you ever want to do solar physics, this is the one thing with which you start your proposal, right, in the introduction. Last year, 40 satellites burned up because of a geomagnetic storm. Because what happens is the geomagnetic storm will warm up Earth's atmosphere, right? It will expand, which means that you will get more air to higher altitudes. So the satellites which were inserted onto their starting orbit were facing more air density than predicted, and as a result they burned up. Very stupid. If they listened to our space forecast, it wouldn't have happened. Okay, I mean, Musk of course calculated with the risk, but it's a very stupid way to lose 40 satellites. Okay, anyway, let's move on. So what we do in Leuven is that we try to look at the magnetic structures on the surface of the sun. We try to predict the global plasma behavior around the sun, right? The solar wind, and then we can issue forecasts like these, right? So we propagate it through the heliosphere, and for different stations which represent the Earth, Mars, and satellites that we have in space, we can predict the behavior of the local plasma conditions and issue forecasts, right? So if you have a satellite here somewhere and we find out, okay, there will be a hit of a coronal mass ejection coming from the sun, you can put it in a safe mode, right? Or you can rotate it so that the most sensitive instruments are shielded a bit better. All right, okay, I'm on time. So before I started doing space weather, and again, this is one of the places where there's a lot of funding, a lot of opportunities. Everybody's doing it because we're realizing that it's very, very important. So if you're into this, let me know and we can find some options. But before I started all of this, I was doing actually hypersonics during my master's, which was master's in engineering actually in Delft. And maybe you wonder how these two are related. But if you're traveling at several kilometers per second speed in space and suddenly you start to descend into the atmosphere, the air gets hotter, so you get a lot of friction, you get a lot of radiation. Afterwards, you get a lot of conduction and convection right in your nose. So you can actually reach temperatures of 10 to 20,000 degrees, or Kelvin. I mean, you're a physicist, so you know these things, right? Around your space shuttle or whatever vehicle you're working on, and that's not nice, especially if you have astronauts inside. That's fairly dangerous. So this kind of hypersonic design is very, very difficult to do, and for that you really have to really well predict the properties of the air plasma actually that you have around it. So basically the same kind of physics that we use for space weather, right? So that's kind of Euler equations or Navier-Stokes equations with Maxwell equations you can use here. You just have to replace hydrogen and helium with air. And actually it gets nastier with air because you have all these subproducts, but hey, what can I do? So we were doing this already in the bachelor's in ESTEC. ESTEC is a very nice place. It's a European Space Agency's technical center in Noordwijk. Fairly windy, not exactly a Spanish beach, but still very nice to go and get a lot of experience. And now we have a nice project going on in the von Karman, is this working? We'll see. Institute in Brussels. Maybe if I go like this, no? I think it will change at some point, or not. Huh. Okay, we will see if this works or not. But yeah, maybe the presentation is too large. Anyway, I will keep talking and then I will show you later. So actually what we do right now in Brussels, there is a von Karman Institute for Fluid Dynamics. And the idea is that I can also show you on this particular picture. When you're re-entering, you have all this plasma around you, right? And this plasma is charged, so it listens to electromagnetic fields. So if you're trying to lower the amount of heating that you get during re-entry, they're looking at implementing electromagnets into the nose tips of these vehicles. And if you apply appropriate magnetic field, you can actually push some of the plasma away from your nose, and in that way you will increase the boundary layer and decrease the heating. You also have issues with radio communication blackout. Maybe you have heard about it. So this plasma around you actually absorbs most kinds of radiation or radio communications that you can get. So as a result, you will not be able to communicate with your re-entering body. So that's not very nice. But what you can do is, again, push the plasma in a certain direction to a certain extent, and then maybe you can reconnect, you can regain the communication signal and get a little bit of a better, safer situation when you're going down the atmosphere. So this is not moving, so I'm not sure if it's my Safari that went down, but I will try to close it and I will try to start it again, and we will see what happens. So that's hypersonics. I think, again, okay, it's not astrophysics, but you still work with plasma, so I can maybe just keep it like this. So you see here the principle of the electromagnet, which can then change the movement of your charges and thus of the air. So if you're interested in this, again, I think there are many nice projects, because whenever you want to go to space and return, you will be facing this very, 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 very hot flow. Next, I will tell you a little bit about engines, ion engines, and plasma electric thrusters, we call it, or ion thrusters, but it's basically all just plasma that we use in space to move. Okay, maybe that's not that related to the things that you saw before, but it looks really good, I promise you, and it's very, very important. So for this, we were in, it's in Norwegian here because reasons, but Tyskland is actually Germany. And for that, me and also actually my boyfriend, we worked in Göttingen in Germany. They have a massive experimental center. For example, they also have hypersonic wind tunnels where they can get up to Mach 30. But anyway, apart from all these other facilities, they also have a 12.5 meters long vacuum chamber. So here you can see an average size person, right? So it's very small compared to the vacuum chamber. And in this vacuum chamber, they are testing ion engines. And if you look at an ion engine, it's still just plasma. You generate plasma from the gas that you carry with you to space. And well, you charge it and then you accelerate it using electrodes or electromagnets. It depends on the type of the engine that you're working with. So again, here you have some kind of kinetic treatment of the fluid, right? So again, fluid equations combined with electromagnetics. So it's something that everybody needs nowadays, right? Because these are the primary engines that we're using on orbit to move around. And you have to certify them, you have to test them. That's why we place them into the vacuum chamber. On the side, you also have the numerical model, right? So you try to determine what it should do. You check what it's actually doing. And then this way you can test your ion engines, and then afterwards you can send them to space. So this was a very nice few months project. But again, if you're looking into places, into fields which definitely will never die out, or at least not in the next 50 years, this can be very interesting for you. And finally, I think one of the most fun but most difficult fields that we currently work with is fusion. So probably you know about the ITER Tokamak project, which is being built in southern France to create the first fusion reactor. Whether it will work out or not, we will see, but they are doing their best, and okay, so far they're progressing nicely. But you don't have to go to ITER down to France, especially if you don't speak French, don't go there, that's a suicide. But there are many other centers, interesting research centers all around Europe that are actually looking at whether what's happening, well, they're actually making predictions for how this plasma in ITER should behave, and how to tweak exactly the magnetic field and electric field in these things so that it works better. So most of the research is actually done at the universities, not down there. Down there, it's really just the construction and the engineering. So we work with two groups. One is Max Planck Institute in Garching, another one is DIFR in Eindhoven. And again, you might think that this is something completely different from space weather or from hypersonics, but not even that much. It's still a stream of plasma, which is obeying fluid equations. In this case, it's gyrokinetic equations, Lassell equations, but again, that's something that you get in your plasma theory course, and Maxwell equations, right? Electromagnetic field. And in this case, just like you get different kind of instabilities in your solar plasma, right? You have all sorts of loop oscillations. Maybe you have seen that in observations. You will get a lot of type of instabilities in these kind of plasmas. So when we work with these applications, we're looking at, okay, we will get some kind of sausage instability, king instability, how to create this plasma such that it is stable and it doesn't touch the walls, right? Because if you touch the walls with something that is 300 million kelvins, the walls do not like it. So we use, again, a similar software for that. And again, this is stability of basically a loop in a huge fusion reactor similarly to how you can study the stability of loops on the sun, right? Again, the equations that you use are slightly different. Here you have to use gyrokinetic approaches. But again, once you learn the plasma theory and once you learn the fluidic descriptions in different regimes, we have not many issues understanding each other when we are using the codes of each other. With this group, right now we are working with differ most of the time. Because, so for example, this is also very nice if you change your fields a little bit, because everybody has kind of their own understanding, their own consensus, but the different fields rarely talk to each other. You know how conferences work, right? You have your very specific conference, and then you don't have a space conference. I mean, you do, but okay, there you don't go to talk about your research specifically, but you always have your own session, your group, where you have some kind of consensus. So for example, my supervisor asked me, he's like, okay, I would want to see what actually electrons are doing in the corona. Like, can electrons create instabilities in solar corona? And that's something that nobody really talks about in solar physics, because we all just together, we all ignore electrons because we just assume quasi-neutrality almost everywhere. We don't even know if it's correct, but it's an assumption that everybody makes. So if you actually want to start studying these things, you have to seek out people who have slightly different understanding, slightly different habits in place. And for example, in fusion reactors, you cannot neglect the separate motion of electrons. That's why we went to Eindhoven in the first place, to ask about their experience with modeling of electrons. And now we're looking at collaboration of how we can model electrons in solar corona. So these kind of interdisciplinary cooperations can really also increase your understanding in your field, as well as, of course, you learn a lot about the other fields and broaden your perspectives as a young astrophysicist or young physicist in general. Before I finish, just a little slide about your options that you want to get, that you maybe can get once you finish your studies or your PhDs or your postdocs. So of course you can go to basically any university, right, for a PhD, for postdoc, for an internship. But there are also space organizations where maybe you can look at. So ESA has student internships, young graduate traineeship programs. Depending on your number of years of experience, you can then start junior professional program. You can have your PhD co-funded by ESA. So these are all options that you can have a look at. And at least once a year, usually there are vacancies in all these different options. There is EUSPA and UNUSA. They are a bit more focused usually on policy and on exploitation of data, but every now and then they actually do need experts from the different fields, so maybe that's something that could be also interesting for you. At least UNUSA is also based in Vienna, so that's very close. And even if there is no nice position in ESA, you want to go abroad and maybe you're looking outside of academia, outside of universities, there are always national programs. So just like you have ESA on the European program, you have on the national programs, the German Space Agency, l'Agenzia Spaziale Italiana, right, that's in Italy, CIRA, etc. So have a look at that, think outside of the box. Now, of course, Slovakia has also Space Office, but they're not really doing research yet, so maybe we need to wait 50 or 500 years for that, we will see. But yeah, that's from my side. I don't want to bother you too much because I think I'm already 2 minutes overdue. So thank you very much for your attention. And if you have any questions regarding what I said, please let me know on my email. Thank you. I can't hear you yet, so. Yes, perfect, thanks.
Sometimes for discussion, so if any. Okay, I would like to ask about those aerodynamics in plasma. Is it possible to simulate them in some plasma tunnel, or is it just numerical simulations?
Yes, so we have different kind of, so you can have a proper hypersonic tunnel where you can recreate Mach 30, for example. That's what they do in DLR in Göttingen. It's actually quite a fun instrument because you accelerate this like half-a-ton piston that then compresses the air, which then expands at Mach 30. So this entire facility is actually put on the first floor so that the entire building can move like this. So when the piston is being accelerated, it's quite something. But that way you can get the Mach regime, but you will not get the temperatures in there. Then you also have plasma tunnels where you can replicate the temperatures and the chemistry of the air that you're dealing with, but you cannot replicate the Mach regime. So it's kind of impossible to get all of it at once unless you literally go to space and drop it and see what happens. But you have this kind of partial test, and then of course on the side you have also numerical modeling. So actually what many times we do is, okay, you know, you cannot 100% replicate the conditions during re-entry on the ground, but you can try to replicate in your numerical solver the conditions in the wind tunnel. So then you have data from the wind tunnel at Mach 30, but okay, lower temperatures, lower enthalpy. And then you have the same simulation, you see how well you can match it. Then you put it to a high enthalpy shock tunnel or plasma tunnel, right? Again, you can recreate this in your numerical code, compare it, and if you get both good agreements, right, in all these two different regimes, you know that your numerical code is doing things right, and then you can use this numerical code to model the entire trajectory in the correct regime as you're going from the Earth. Of course, you have to, we're engineers, so you always have to multiply by 2 just in case. There are all these different things that you cannot count with, especially if you have people there, like actually living human beings. You probably don't want to count on some. So for example, Space Shuttle, in the beginning, they had to, I think it was almost twice the deflections that they had to apply during re-entry than what was predicted because of chemistry of air that they did not take into account properly. And just like having a bad chemical model of the air could have almost killed them, right? So despite our best understanding, you have to still apply some safety factors. But yeah, with the combination of the ground facilities like the wind tunnels, the high and low enthalpy wind tunnels, and the numerical codes, you can more or less get a good guess of what's going to happen.
Great, thank you. Any more questions?
Good question about the space weather. Don't you know if there is any team in Europe which is trying to research and study the effects on the artificial materials of these high energy particles? I know that in America, the JPL has whole office for that, but if also in ESA or any other European research institution, there is somebody who is testing and this part.
Honestly, I have no clue. So you're looking at the flux, the particle flux effect on
long-term exposure of the artificial material for 20 years or something like that on georing, and how it will affect it.
Yeah, honestly, I have no clue. I didn't do structures too much, but I would be surprised if this is not done. So, for example, in Göttingen, I saw what they do is that they are looking at the effect of, so when you have ion thruster, to some extent, you have a charged plume coming out of your spacecraft, so some of it wants to return, right? And if this happens, if it's not properly neutralized, you will get this flux of ions, many times high energy, not as much as space ions, but still high energy ions attacking your spacecraft materials from the top. And they do a lot of research on that because then that degrades the performance of your materials and your structure, and over time you might lose quite a lot of material. I haven't seen that this would be done with space weather yet, but I would be surprised if it's not so. I think you just have to look a bit. But yeah, I'm not a structures person, so maybe you can also just send me an email and we can look at it together.
Yeah, I know this one from America, this team around Gelhard and Hoffman. Mm-hmm. I wrote about it, but I didn't publish the European team.
I think you can just look at their papers and look at the introduction. Many times they also mention what is done in other places, especially if you get a reviewer from another place, they want to be cited, you know how it works. So, and maybe then also looking at the conferences they go to, I would assume then that's kind of the community that is dealing with all of this. And I cannot imagine that Europeans would not be doing this, especially the structures people. So I think probably it's done somewhere, but I can't tell you where, sorry.
Okay, thank you.
Agnieszka, so when we are to see in Bratislava?
Sorry, I can't hear too well. Huh?
When we are going to see you in Bratislava?
When I'm going to what?
Bratislava.
Oh, yeah, we will see. I have no clue. It's kind of random, and whenever I come. So at latest summer, maybe before, we will see. And the last month I found out 3 days before, so leave it as a surprise, huh?
Right.
Okay, thank you very much.
Okay, thanks a lot. Thanks for having me.
And goodbye.
Okay, bye-bye.
Bye.